So we are back talking about your most favorite thing in the entire world, and that's electron configuration. And in the last video, this is where we ended up. So I was taking baby steps. I was going through and I was doing one element at a time, and I started up at the top, and we did the electron configuration for hydrogen and helium and lithium and carbon and magnesium. So I told you in this video we're going to go even further. And the reason is because we now know that D's and F's can cause us a problem. Not only can that cause us a problem with our final grades at the end of the semester, no one wants D's and F's, but it's going to cause us a problem as well in electron configuration. And we have to remember that. We have to remember to correct for that. So I told you that we would do a few more examples of electron configuration using D and using F throughout this process. All right. So I want to do the electron configuration for iodine. Iodine's number 53. Now, you might be making fun of how I pronounce iodine, but let's go up to the top and let's read down. These things are trended, right? Fluorine, chlorine, bromine, iodine, astatine. Now, does that kind of make sense? If you want to call it iodine, then you can, but fluorine, chlorine, bromine, iodine, astatine. I think that fits the trend a little bit better, which is why I say iodine and not iodine for that element. So let's do the electron configuration for iodine. And I'm going to do it right here on this periodic chart. So let me erase all of this up here at the top, and this is where we'll start, so that way you can follow through with me. And we'll go ahead and start. So, iodine, or iodine. We'll start up at the top with 1. We start off in the S block, S, and there's hydrogen and helium, so there's 2 of them. Then we go to the second row, 2. We start off in the S block, S, and that's lithium and beryllium, so there's 2 of those. We then jump over to the green section. Remember, that's P. But when I do that and I switch subshells, we said we have to write down the period number again. So there's a 2. This time I'm in P. And 1, 2, 3, 4, 5, 6, all the way across. We read it like a book. So 2P6. The next period down is number 3. We start off in the S block. That's sodium and magnesium, so that's 3S2. We then jump over to the green block with aluminum at number 13. Well, we're in a different subshell. We write down 3 again. We're now in the P block. And if I count over, 1, 2, 3, 4, 5, 6. So there you go. We now go to the 4th row, or the 4th period. So I write down 4. I start off in the S block. There we go. And that's potassium and calcium. So there's 2 of them. So 4S2. I then go into the blue area. That blue transition valley element block, that is my D block. And remember, D's fall 1 behind. Why? We'll figure that out later. So instead of writing 4D, I'm actually going to write 3D. And we count over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that ends us up with zinc. I then go into the green block. That is my P block one more time. Well, P's are normal numbers. So I write down 4 because we're in the 4th row. I write down P because we're in the P block. And I count over. 1, 2, 3, 4, 5, 6. So 4P6. Still not finished, but I'm going to have to continue this on a separate line. Otherwise, I would just chain this out into one big line item. But now I'm in the 5th row, or the 5th period, so I'll write down 5. I'm in the S block, so there's my S. And rubidium and strontium, there's my 2, so 5S2. I then go to the transition valley. That is my D block, but this is not a 5D. D's fall one behind. So this is a 4D. And I count across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That ends up with cadmium, 4D10. I then transition over to the P subshell. This goes back to regular number because P's match the period number. So this goes back to 5. We are now back in P. And to iodine, 1, 2, 3, 4, 5. 5, P5. So the electron configuration of iodine is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p5. And that is your electron map representing every electron in iodine. Where is it located? What orbit? And what subshell? So what does this actually mean, right? We've not done an F example. We'll get there. But I want to take a pause here and I want to talk about what this actually represents. Well, this represents 2 electrons are in that first orbit around the nucleus, and they go around it in a spherical fashion. 2 more electrons are in the next layer outside of the nucleus, and they travel in a spherical fashion. Then we have 6 electrons in that same layer that travel around the nucleus in a figure 8. 2 electrons in the third layer in a spherical subshell. 6 electrons in that same layer that travel in a figure 8 subshell. 2 electrons in the fourth layer of the onion that goes spherical. 10 electrons back in that third layer that do the 4-leaf clover, and so forth. This gives us a general map, a kind of an idea of how these electrons are arranged in the atom. And I know that for some of you, you're thinking, well, why is this important? And honestly, after this first lecture module, we will rarely go back to electron configuration again. But it is a staple. It is a foundation in chemistry. It's a foundation in organic. It's assumed that we know what this stuff is and what it does, because this allows us to start talking about more advanced topics in organic when we need to talk about those advanced topics in organic. So we're putting the foundation now. And then later on, we might come back to this, but if we do, it will be very few and far between. In other words, just grit and bear through this right now, because if you can, you will probably rarely will see this again. All right, so there's the electron configuration for iodine. Okay, so now let's do an example with F. And this means that we're going to have to go all the way down to the bottom of the chart, right? And we're going to start all the way up to the top. That's what I like to do. I like to give you the repeat segments over and over and over so you feel more comfortable with them. So let's go and do something like uranium number 92. Ooh, this one's going to be a doozy, folks, so bear with me. So number 92 is down here at the very bottom. That is uranium. We need to do the electron configuration of this. And I want you to always start up here at the very top and work yourselves down. I don't like the shortcuts that some people do. And the reason is because I think doing this repetitively gets you more comfortable with electron configuration versus the shortcut method. Shortcut method can come later after you master the electron configuration. But once you start learning it, we always start up to the top and we work ourselves down to the bottom. So let's start off in period 1, S, 2 of them. Then I go to period 2, S, 2 of those. Then I go in the same period, I'm in the P block, and there's 6 of those. I'm now in the third row, S block, there's 2 of them. I then skip to the third row, P block, and there's 6 of them. I then skip to the 4th row, S block, and there's 2 of them. That leaves me with calcium at this point. I now venture to the D category. D's fall 1 behind. Therefore, this is not a 4D. This is a 3D. And I count the number in the D section, and there's 10 of them. I then go back to number 4. I'm in my P block, and there's 6. I'm now in the 5th row. 5th row, I start off in the S block, rubidium and strontium, 2. I now go to the D block. D's fall 1 behind. Therefore, this is not 5D, this is 4D. And if I count across, there's 10 of them, so 4D10. That leaves me at cadmium. I then go back to the P block, so we're back at 5. P, and I count all the way across because I need to go further down the chart. So 5P6. I'm now in the 6th period, so I'm going to write a 6. I start off in the S block with cesium. So there's S, and there's 2 of them there, cesium and barium, so 6S2. Now notice number 57 is blank, and number 57 says, whoa, 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 you go down here to the bottom. And then you have to include this bottom row before you really go back up to the D block. What that means is that it looks like the F's are written before the D's. Notice it says 57 through 71, and we are going in order. So after 56 barium, 57 is the next number. 57 starts down here at the F block. Well, F's fall 2 behind, not 1 behind. So normally, this is in the 6th row, and it's not a 6F. It falls 2 behind, which makes it a 4F. And then you count across. We need to get to uranium, so we need to go to the next row below. So we need to include everything here. So if I count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's 14 of them. And then I go back up to the top, and I'm going to include the D's at this point. All right. If I include the D's, I now go 1 behind, and there's a total of 10 of those. I'm now back into the 6th row. It matches the row number P block, and I include all 6 of those, and that works me up to radon. Then I'm in the 7th period, S2, and then I go down to the F block, and that F block looks like it's 1, 2, 3, 4 over in order for me to get to uranium. All right, so that F block falls 2 behind. It's not a 7F. This is a 5F, and then I count 4 over. So this is the way this periodic chart is made. This is the way that it's structured and organized, okay? But you're also going to find a periodic table that will be a little different here. If you look down here below and we count across 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. The 57, some charts will put the LA actually there, and the AC actually here, and it leaves it off of these rows. Okay? So what they would do is that they would say the LA is in the D block, so therefore this is 6S2, then this would be 5D1, and then it goes to 4F14, and then it goes back to the 5D to finish out the remaining 9. That depends on what periodic chart that you have. And the good news for you is that I will rarely ask you to go this far in the periodic chart. But I think it's good for you to see one of these examples and kind of trigger a memory about how to get and handle the D's and the F's in the electron configuration. All right? I'm not done with electron configuration, though. So what do I want to talk about it now? Well, let's take a look at something like magnesium that we've done before. What I would like for you to do is look at this electron configuration and add up all of the electrons. Double check yourself, folks. How do I add up the electrons? You look at the superscripts and you add all those numbers up. There's a 2 plus 6 is 8, plus 2 more, 10, plus 2 more, 12. So this electron configuration is saying that magnesium has 12 electrons. Okay, well, does it? Well, we'll go to the periodic chart. Here's magnesium, and look, there's the atomic number, and that atomic number is 12. So that's a very good sign that you did the electron configuration the proper way. Look at carbon. Here's the electron configuration for carbon. Add up your superscripts. 2, 3, 4, 5, 6. On the periodic chart, we hope that carbon has 6 electrons, and it does, because it has the atomic number of 6. Helium, 1s2. That's all it is. Add up your subscripts or superscripts. Well, there's a 2 there. We hope that helium has 2 electrons. And if we go to the chart and we look up at the atomic number, sure enough, it does. So that's one of the ways that we can check to make sure that the electron configuration is proper. The other thing that we can do is also check the number of valence electrons. So remember, I told you that the atom has a nucleus, and this nucleus, we have orbits that go around it like onion layers, and we said that anything on the outside layer, if it's an electron, would be classified as a valence electron. Anything on the inside is going to be called a core. Electron configurations give you an idea of the valence electron count. How do we do that? Well, you look at the big coefficient numbers out in front. Look at magnesium here. There's a 1, there's a big 2, there's a big 2, and there's a big 3. So my advice to you is look at your largest coefficient number, and that would be 3 in magnesium's case, and how many electrons are in the last or the biggest coefficient. And there's 2 of them that are there. All the others are paired up with the 2s and the 1s, which is a smaller value. So this gives us an idea that there's 2 electrons in the largest outside shell. So maybe this thing has 2 valence. I can look at the electron configuration to determine that. If I go back to the periodic chart, I see magnesium here. I go up to the top at the group number, and what do I see? There's a 2. That 2 represents the 2 electrons that are in the outside shell of that atom. Carbon would be done the same way. Look at your big coefficient values. So the biggest here is going to be a 2, but it's showing up twice. So I need to add both of those up because both of those are in the outside shell. 2 of them are in spherical fashion, 2 of them are in a figure 8 fashion, but they're both in the outside shell. So 2 plus 2 is 4. So this gives me an idea that carbon has 4 valence. If I go back to the periodic chart, I see carbon, I go up to the top, look at what I see. There is the 4 that is there. That 4 represents the valence. I know where those valences are. Those valences, 2 of them are in the S, 2 of them are in the P, in the outside layer here, which is period number 2. Helium works the same way. Hydrogen works the same way. Pretty much all of them work the same way, except for transitions. Transitions get a little wonky on us, and that's why I like to stay away from those in organic. We will rarely work with the transitions. Maybe once throughout 2 semesters worth of organic will we start including transition metals into the picture. But For the most part, all of my group A's, the 2 columns to the left and the 6 columns to the right, they all work very similar. Okay, so there's the story with electron configuration, and I hope at this point that this is something that you feel a little bit better with as far as comparing it to the general chemistry class. Here's an idea of what the S subshells will look like. Again, this is 2-dimensional because it's drawn. It's not 3-dimensional. But you can see 1s and 2s and 3s are represented, and they get bigger and bigger and bigger as far as getting away from the nucleus or the core of the atom. Here we see the P's. The P is really a figure 8, but, quite honestly, there are ways to draw a figure 8, and all 3 of those are represented on the screen for you. So in the next video, we're going to pick up from this concept. There is an option. There is an option on how I draw the figure 8. I've been drawing it up and down like this, but someone else might draw it a completely different way because it is 3-dimensional. So does it go up and down? Does it go left and right? Does it go toward me and away from me? Those are the questions that we're going to have to start talking about and providing you answers to. So in the next video, that is where we'll start, and we'll address this concept of orbits one more time.